All right, good afternoon. Um, this is a talk on OCP NIC 3.0 management with NCSI 1.2. It's a little bit in our collaboration with NIC subgroup, and it is related to hardware management. That's why it is in this track. I'll be presenting this with my colleague Bob. I'm Hamel, architect from Broadcom, and Bob, who is on the Zoom from Dell. We both are hardware management project co-leads. So I'll kick it off, go over, introduce the OCP NIC 3.0 manageability features, and then talk about what's in there, and then we'll introduce how we leverage the existing standards. And then Bob will cover specifically the NCSI aspect of that. Okay, so OCP NIC 3.0, just quick intro on this. This effort started in Open Compute Project in 2018. It took about 3.5 years to define this. Pretty comprehensive spec, covers all different aspects of a NIC, from the form factors, signals, pin definition, to security and manageability features. One of the main piece of this specification was standards-based manageability, and we had a set of features which are based on existing standard. So it gives a common capability for anybody who is compliant to OCP NIC 3.0 feature set, that how you can manage those devices. So that was one of the key aspects, and in this talk we'll zoom into that. So just like any manageability, first of all this management data transfer you are doing, whether it's a sensor data or doing some control operation, collecting some telemetry data, the underlying transport, that's where you want to have something which is based on standard. DMTF are another standard organization which works very closely with OCP. Has standardized couple of management transport. One is based on RMII. This is a sideband interface which is derived from RMII and standardized by DMTF. What that allows you to have is a BMC can have point-to-point connection with NIC through that interface, and the transport is based on all the Ethernet frame and the control traffic that is defined on top of that. So that's one transport. Other one is MCTP, which stands for Management Component Transport Protocol. This is medium independent transport that is defined, which contains very simple packetization of messages, basic fragmentation reassembly, and capability to have logical addressing. So MCTP, today, there are a number of binding defines. It can run over SM bus or PCI VDM, and there are more bindings being defined. So those were the two key transports. The way OCP NIC 3.0 spec leveraged those is it created 3 different management type. And what this enabled, what is listed here, is an implementation which supports RBT, RMII-based transport, or MCTP-based transport is compliant to the spec. And implementation can also support both. For example, if your NIC is connected through RMII-based transport to BMC, in addition, it has SM bus or PCI VDM connectivity. Then in different power state, it can go through different interfaces. That's one use case. You can use for your pass-through and other traffic RMII-based transport, but maybe for thermal monitoring, you are using MCTP or SM bus. So in summary, using this kind of standard transport gives you one common data transfer mechanism for your management data, but it also gives you flexibility in terms of over what medium you can run this traffic over. So this is currently in the OCP NIC 3.0 spec. It allows for existing implementation to pick one of the management type. Specifically, RMII-based transport, that definition comes from NCSI spec, which we'll dive into details. Before we go there, I want to talk about some of the key features that OCP NIC 3.0 had. So the first one covers the use case where there are BMC implementation. When you use the shared NIC model, what I mean by shared NIC is the NIC is being used for the host traffic as well as it's being shared by the BMC to run the management traffic. There is no separate network port that is being used for management. When you do that, there are requirements that BMC implementation, some of the BMC implementation, that they don't want to provision MAC addresses for the management traffic. So they rely on the NICs to provision that. So that was one of the feature that got defined in OCP NIC 3.0, that how you can provision those MAC addresses, what kind of MAC address numbering scheme, which allows you to have a standard scheme, and also a common way to retrieve that using NCSI interface. So that's the provisioning aspect of BMC MAC addresses. Then BMC, the core set of things that any device they want to do from the monitoring standpoint is monitors temperature. What is the capability that this device has in terms of power consumption? So there are, here also it's leveraging standard platform level data model standard, which allows it to monitor temperature. NCSI also has temperature monitoring capability, and NCSI can also run PLDM traffic over RMII based transport. So those were the two monitoring type of features. And then, like any device today, you take, whether it's a NIC or non-NIC, which are compliant to OCP NIC 3.0 as we are expanding into other accelerator or other devices. All of them, they have some kind of software firmware running on those devices. It's very important how you manage that. So for that, you need standard way to get to the firmware inventory as well as ability to do update completely out of band. And there are standard mechanism defined there where you can use one of the transport defined and then use PLDM kind of model to update the firmware in one interoperable way. So that those are more from the standpoint of how you manage the device from the inventory standpoint as well as update the firmware. And the last thing what we did, which we didn't have in previous OCP MAS or NIC spec, is the FRU definition was left up to the implementation. And it may sound very simple that what's the big deal in that, but it's important to have one common way to have that FRU definition. And why it's important is FRU information gives you things here like this device, what transport does it support, what kind of thermal envelope it fits into, its SM-bus capability. So what OCP NIC 3.0 spec did is standardize that FRU content format. That way, every implementation which supports OCP NIC 3.0, you can count on the common FRU definition. So with that, those are all the OCP NIC 3.0 manageability features. What we are going to do in next few slides, and I'm going to hand it to Bob, is to introduce NCSI and how that relates to the OCP NIC 3.0 manageability features. And as a part of this collaboration between Open Compute and DMTF, some of the requirements came from OCP NIC 3.0 definition, which went into the latest NCSI work in progress spec, which is 1.2, and we are seeking feedback there. So with that, let me hand it to Bob. Bob?
Thank you, Hemel, and good afternoon, everybody. So kind of as partially as a refresher, because NCSI has been around for a long time, you know, the fundamental features that it has are this ability to handle pass-through traffic between the BMC and the connected network. It does commands and responses driven by the BMC. And then it also has a definition of notifications, or otherwise known as alerting. You know, those have been in the standard for since its inception, but you know, we're also greatly enhancing that in the version 1.2 edition that I'll get to in a little bit. Recapping, you know, the physical layer implementations as Hemel described earlier, we have NCSI over RBT, which stands for RMII-based transport. It also has the provisioning, unlike RMII, for hardware arbitration, so that you can have multiple devices on one RBT segment. And you know, all of those are really handling Ethernet type traffic. NCSI over MCTP uses the NCSI, let's call it API, the commands and response definition and the alerting definition to run over MCTP over some other physical layer. And so those other physical layers could be SM bus, it could be PCI VDM, and recently I3C has been defined as a binding for NCSI. And so, you know, different physical layers, you know, through using MCTP, you know, have the ability to support NCSI operations. As previously stated, OCP NIC 3.0 specification defines operation over both RBT and MCTP over the physical layers that MCTP runs on. It defines the package addressing, which is how you differentiate the different NCSI endpoints from the BMC on one RBT segment. And likewise for MCTP, we would use MCTP addressing in that case for operation over non-RBT physical layers. The NIC 3.0 spec, you know, defines pins on the connector for both SM bus and RBT. Does not define pins for I3C specifically. And then there are timings specified in the NIC 3.0 spec to aid interoperability between the folks defining or designing the motherboards and those defining the adapters. The NCSI spec itself doesn't do that. It gives end-to-end specifications for timing. But you know, as it was important in the definition of the MES 3.0 standard, the arbitration of who gets what from a timing point of view became important. And so, you know, those parameters, you know, are defined there, but not in NCSI itself. Likewise for the routing guidelines, how, you know, one handles NCSI clocking and other routing, including the potential for hot plug as we go forward. It's important to understand who's responsible for doing what part of that implementation. Okay, next slide, please.
Okay. So as you can see, the OCP NIC 3.0, how it leveraged the NCSI spec. Let's go to the next slide.
So version 1.2 of NCSI specifically greatly enhances the previous versions of NCSI to handle many things that have evolved over the past 10 years in network controllers. As someone described, gives you the ability to retrieve a BMC MAC address from the NIC for the BMC to use, if that's the desired way of doing things. There is reporting of temperatures from ASICs, the network controller itself, the ambient temperature that the card environment is seeing, the SFF module temperature if you're using an optical transport for your networking. NCSI 1.2 provides the ability to read that information out of the optical module and report it back to the BMC so that we can monitor that and make sure that it is also within its thermal profile. And then there's also been a lot of enhancements on the link status reporting that is present in the 1.2 spec. Many new speeds up to 400 gigabits per second are defined. The PHY configuration and the interface with the optical modules are all now included in NCSI 1.2 proper. There have been other extensions that we've added to 1.2. PLDM over RBT was not previously defined or supported, but for those devices that do things in PLDM that are not supported or defined in NCSI itself, there's the ability to do PLDM operations, including firmware update over NCSI RBT. Since a number of network controllers these days support partitioning of the NIC onto one physical port, there's many different management structures in NCSI 1.2 to handle that definition. NCSI 1.2 also includes the support for fiber channel controllers and InfiniBand controllers. And so as they have their own specific boot configuration settings and link status, link configuration settings, all of those are now included in NCSI 1.2. So, NCSI now is, truly independent of, networking fabric that you might choose, because it can do Ethernet, it can do fiber channel, and it can do InfiniBand, all as defined in the 1.2 version. So those are the highlights of things that are being included in the 1.2 spec. So Hemel, I will give it back to you for a final wrap up for the next couple minutes.
All right, thanks, Bob. So in this talk, we talked about the OCP 3.0 manageability features based on DMTF standard and how some of those use cases fed into NCSI 1.2. So call to action here is NCSI 1.2 is still being standardized. So provide your feedback to that spec as well as OCP NIC 3.0 spec. Contribute to those. Look for any consideration that we can have in this version or even going forward. With that, I'm going to conclude. I may have a time for one quick question. Go ahead.
Yeah, one quick question. Does the NCSI allow reading config space, PCI config space from the NIC device?
So the question is, does NCSI allow reading PCI config space? The answer is no today, but there is nothing from the protocol standpoint which will prevent that. We just don't have that kind of command set where you can directly read the PCI config space using NCSI commands. But that's an interesting idea. What's the use case there is like some of the information is already available, right, through other commands.
Yeah, so from the BMC, if you want to monitor certain aspects of the PCI interface, and even sometimes control, say secondary bus reset, then that would be an interesting way to achieve that. Today there is no direct way. We kind of go through CPU and then Southbridge and all kind of complex way. So this will be very good, interesting way to. Another question, follow-up question is, and I think the answer probably no. Can we sniff into data packets?
Over NCSI.
Mm-hmm.
Today, it only allows you to have management traffic over
Good so
NCSI
far.
Fast.
And I'm done for the day, so thanks for your help.
Okay.
So yeah, I think that is another, again, the capability is there to indicate that kind of commands, but today's focus has only been on management traffic, not the host traffic. Host traffic, you can get the statistic, but not actual data.
Yes. So one use case here we were talking about the timing information, network timing information.
PTP, yeah.
PTP. I forgot that acronym.
PTP, yes.
Yeah. So today the BMC and all the Linux running there, right? The timing, the clock is a different timing than the host and the rest of the infrastructure, and there is no good way to synchronize. So this could be another way where if we can access the config space and then get the time information, or maybe sniff into packets and get the timing information, then we can synchronize the clock on the BMC side also.
Right. No, I think that's a good question. So in general, we have extended NCSI to include more traffic to be filtered also to BMC. So this may fall in same category. With that, I'm getting signal. I'm done. Thanks, everyone.